Okay, guys, for 10.3, we are going to work some more with quadratics, and we're going to emphasize some of the imaginary number aspects that quadratics can give. Three styles of problems that this section is going to ask you. You notice that it has a lengthy title. We're going to find quadratic equations given the solutions, and then we're going to factor quadratics that we used to call prime. We're going to kind of force factor them using imaginary numbers, because stuff that doesn't, that we traditionally would call prime, there are still things that could multiply together to make that, especially given that we're allowed to use i's in this section. So let's start with the first style. There's some problems that are just strictly review, and for example, just solving quadratic equations. So let's start with a nice basic one. X squared minus 10x plus 27 is equal to 0. Now, this is just basically a review of either factoring or quadratic formula and using i's if necessary. This one's not going to factor, so I'm going to go on to the quadratic formula. Negative b, which is 10, plus or minus the square root of b squared, which is 100, minus 4 times 1 times 27, all over 2. 4 times 27 would be 108. So this is 10 plus or minus the square root of negative 8 over 2. And let's see, the square root of negative 8 can be simplified to 2i radical 2. And since all of those parts have a 2 in them, we can call this 5 plus or minus I radical 2 by simplifying all of those. You can only do that if all three parts work. So my two solutions are 5 plus or minus I radical 2. And remember, these aren't x-intercepts. This particular parabola would float around somewhere above the axis. I don't know if that's exactly where it would go, but it does not touch the x-axis. But there are two values that will make it equal to 0, which are these two imaginary values, 5 plus I radical 2 and 5 minus I radical 2. So that's the first section of homework problems. The second section is giving you the two solutions find the quadratic. And in the section, it goes through the derivation of these two formulas. It uses S1 and S2. That just kind of, I don't like that, because that requires you to remember some formulas. Here's the way I prefer to do these problems. If you would like to check out section 10.3 and read about these two formulas, it might save you 10 seconds on the test, but it's going to require you to remember a couple other formulas. So here's what I would do. If they give you two real solutions like this, 4 and negative 3. We have talked at length about how the solutions and the factors of a quadratic are connected. If they give you 4 and negative 3, then your two factors are x minus 4 and x plus 3, the opposite signs of what they have. And then you would FOIL that out and get the quadratic that goes with it. So I'm not going to do that, because that's really old stuff. Now, what if they give you an imaginary, like 2 plus 3i? Well, first of all, they only have to give you one, because our imaginary, our complex roots always come in conjugate pairs. When you do the quadratic formula, you're always going to have the plus or minus 3i set up before you get to this point. So if they tell you one, a fact about imaginary solutions is they come in conjugate pairs. Now, here's the way I would approach this problem. Just like you did with those two real numbers, subtract both of those from x. Remember that when you subtract those, the negative has to distribute to both parts. So what I'm going to do is multiply together x minus 2 minus 3i, and x minus 2 plus 3i, because that negative distributes to both parts in both of those terms. Now I'm going to, technically it's not foiling because it's not FOIL, but I'm going to multiply each one in the first by each one in the second. So I'm going to distribute my x through and get x squared minus 2x plus 3ix. I'm going to distribute my negative 2 through, and I'm going to get negative 2x plus 4 minus 6i. Then I'm going to distribute my negative 3i and get negative 3ix plus 6i minus 9i squared. All right, so all I was doing is multiplying out everything. Now, what you'll notice is I have a plus 3ix and a minus 3ix, a plus 6i and a minus 6i, and then everything else should form together to make a nice quadratic. I've got an x squared, I've got a negative 2x and a negative 2x that together make a negative 4x. And then I've got a plus 4 and a negative 9i squared. Remember that an I squared changes a sign, so that's the same as plus 9, which makes this plus 13. So if the question is, the only thing they have to say is find the quadratic that has this solution. Your steps would be to find the other solution by just finding the conjugate, subtract them both from x, and then just do a lot of multiplying. Just for kicks, just to check and make sure this worked, if this were your original, the quadratic formula would produce negative b plus or minus the square root of b squared minus 4 times 1 times 13 all over 2. 4 times 13 is 52. 16 minus 52 is negative 44. Wait a second, no it's not. 16 minus 52 is negative 36. So what I have is x equals 4 plus or minus square root of negative 36 is 6i over 2 is 2 plus or minus 3i. So I've just confirmed my two answers. So that's style of the question number 2, where it gives you roots and you do x minus each one and then multiply. Okay, next. I'm going to call this section force factoring, because up until now you would have looked at these questions and just said, that's prime. For example, x squared plus 10x plus 29. Okay, you can factor stuff. Factor means to break it down into parts that would multiply together to produce the original. So the number 7, we would say 7 is prime because it can't really factor it into anything except 7 and 1. But 2 times 3.5 does make 7, so I would consider that what I would call force factoring 7. We're going to do that with this quadratic. To factor, the connection between zeros and factors is the same thing we're doing here. If 4 is a 0, then x minus 4 is a factor, and that works for imaginaries too. So let's find the two zeros. Negative b plus or minus square root of b squared minus 4 times 1 times 29. And let's see, 4 times 29 is, I believe, 116. So altogether, that's negative 16 over 2, or negative 10 plus or minus 4i over 2, or negative 5 plus or minus 2i. So this is a quadratic. It has to have two zeros, and there are the two zeros. Now, when you know zeros, you also know factors, because x minus the 0 is a factor. So we can force factor this quadratic into x minus one of the zeros, which is negative 5 plus 2i, times x minus the other 0, negative 5 minus 2i. All right, x minus 0 times x minus 0. Just as if they were 3 and 4, it would be x minus 3, x minus 4. Now distribute the negative, x plus 5 minus 2i times x plus 5 plus 2i, and that's factored. So it's not pretty factoring. You know, you normally would just call that prime, but since we're able to deal with imaginaries now, we'll just say that's how you can factor. Which, by the way, leads to one little subtopic. You've never factored a sum of squares before, but allowing you to use imaginaries, we could write this that way, if you agree. An I squared just changes the sign. So you can throw an I squared in and change the sign, which makes this 2x plus 6i and 2x minus 6i. All right, because we would have a difference of two squares. It's just that the second square happens to involve I, which normally we did not do. Okay, so that's three kind of different spins on old quadratic stuff, just allowing the i's to be a part of it. And that'll do it. So we'll talk more about this in class. I'll see you then. Have a good one. Young out.